Hi, my name is Michaels. I'm founder and president of CENOS Simulation software. Today, I would like to walk you through our software and show how our users use it for coil design. Like other simulation software, CENOS consists of three parts, which represent three steps of modeling. The first, users start with geometry settings. Then they define physical parameters like frequency, power, materials, and so on. And of course, as the last step, users see results in order to make design decisions. However, unlike other software, our software uses the best of open source algorithms behind each of these three steps. Therefore, we have slightly different interface for results, geometry, and physical settings. In this video, I would like to walk you through all three steps, but starting with the results and then going in the reverse direction. So let's start with result and see one simulation example. Here we are. So this is a single shot hardening case, and CV joint is hardened in this case. Let me walk you through this interface just to show how our user analyzes results. So first of all, you can see here 3D rendering. You just can simply rotate it. You can zoom in, zoom out. And you can also disable some parts of the geometry like workpiece, inductor, concentrator, or just get them back. In each of these geometries, so you can see different views. Like for example, in workpiece now you can see temperature field. You also can see magnetic flux density, current density, heat, Joule heat, and so on. And the same goes for other parts, like let's, for example, jump into the inductor. And in the inductor, you might be interested in temperature or in current density, for example. So in case of current density, you can clearly see here two hot spots. So that could be potential failure points of the inductor. And in order to make design decision, let's look on the concentrator, and here we go. So we see that the flux concentrators are just next to these hotspots. It's clearly that actually, while designing the concentrators, we probably would like to avoid this kind of design in order to be sure that our inductor will be not heated to the critical points and will be not affected by concentrator design. So, of course, you can also just walk in the time. So here you can see time scale. You just can simply walk back and forth. Let us just make the small video. So this is the video of heating. In this case, inductor is rotating. It could be vice versa. So workpiece can rotate. By the way, our customer really love these videos because they show it for their customers. I recently have been told by one of our customers in California that thanks to this video demonstration, they were able to convince the Boeing engineers to place the order to them. Actually, they overcompete other companies producing induction heating design just because they were able to convince engineers at Boeing factory that they know what they do. And they did it showing the videos and pictures like here. All right, just let me continue my presentation here. Beside this 3D view, you can also see here 2D representation. Actually, this is the cross section of the workpiece. Just to show you, actually, you can make the cross section in any other direction. So this is just the view of the cross section. You just can simply drag this in order to find the right position of your cross section. In this case, we already did two cross sections. So this is vertical cross section, and this is horizontal cross section of the part with splines. The same. You can see here temperature field. You can also change to another field. Here, it's not a problem. The most important is this white line. Actually, this line represents the hardening depth. So without this line, you can see it like this. However, we just apply hardening profile filter, and we see the region which is hardened. So the filter works based on temperature. So you set up austenization temperature and as a threshold temperature, and the filter just show you the region which was effectively heated above this temperature. That means if your cooling or quenching was designed properly, the most probably you will get martensitic structure here in this area. Of course, you can also measure it. So you can see there are two rulers here. Let me show how it works. You can just simply change the position of these 2 points in order to measure the distance. So that, like this. So I just press apply and see the value, the depth of the case. So this is in millimeters. We are a European company, that's why I'm showing you everything in meters. So in this case, it's 3.8 millimeters. However, you can simply change settings and make this in each the same as Fahrenheit for temperature. The same goes for this vertical cross section, and here you can see also temperature over time. We just put 1 point. In this case, it was on the spline, and represent temperature over time in this point. You can put this point anywhere and make this presentation for your particular point. Moreover, you can also draw the line and represent here temperature over line as well. There are plenty other filters. If we look here and go to alphabetic, you can see literary. So this software can represent whatever you want. This is the most powerful post-processing tool. It's called ParaView. It's open source, and our platform ensures full integration of it and give you opportunity to use the best post-processing and visualization tool to show your results, to make design decision based on data. So our customers just look on these results and make the next step, the next design decision. If your case depth here is not enough in some point, like for example here, it's not enough for you. Well, you know that you can make some hypothesis of what you can change. Like, so for example, you can change frequency, or you can change power, you can change design of the coil, or design of flux concentrator, and go back and run simulation again. And now let's go one step back in the physical settings in order to show, and we will show you how easy it is to set up simulation case. So I'm back now in the main interface, and we will go to this middle part, which called physics. So just pressing this button and go in. So let me walk you through Actually, on the left-hand side, you can see 3D rendering on the object. Now you can see just the box because it's air box around. Here, you can see several tabs, and those tabs represent different objects. So in the very beginning, you define objects or domains. In this case, they are workpiece, inductor, concentrator, air, and then they appear here as a tabs. So let's go in each of these tabs and just follow 3 simple steps in order to define your simulation case. Actually, it's really very easy, and the learning curve for this software is very steep. Our Mexican customer just said that it's the fastest learning curve ever. I mean, really, so you can start simple cases in several minutes, but for 3D case like this, the most probably your engineer will need the several days of training, and in 1 week, it will be ready to run simulations and make analysis without any help. All right, so in each of these domain, I will show you simple 3 steps. The first, you have to select what kind of physics you want to simulate in this domain. In this case, you can see that electromagnetics and thermal are enabled. So if we go to inductor, for example, you might not be interested in temperature distribution in inductor, and that's why it's disabled here to save some calculation time. But if you still want to see temperature in inductor, just simply enable it, and that is. Let's go back to workpiece. So in the first step, you also select what kind of electromagnetic domain is it. So it's conductive for workpiece, electrically conductive. It's non-conductive for concentrator, for example. It will be current source for inductor. It could be also voltage source. There will be setting I will show you in a minute. We also have some permanent magnets and surface impedance, and also stranded coil source. It could be not applicable for your business. However, if you work with the stranded coils or you work with a high frequency, so the surface impedance domain might really help you to run simulations fast. But if you're interested in this particular domain, just let me know in the comments or reach out to our sales department, and we will definitely show you another presentation for that. The second step is selection of material. Let's go to our library. So we have library of materials. This library includes some Fluxtrol materials, different types. We work together with the Fluxtrol company, and they provide us up-to-date, so the fresh data for their materials. So that's why it's very useful to use these concentrators. Then for steels, we have high carbon steel 1080, sorry. This is Inconel as well. So we have low carbon steel 1008, low carbon 1020. We have also medium carbon 1045 and some other materials. But anyway, if you not find your material here, it's not a big deal. So you can just simply click new and create your own material. Even more, you can just, let's say, select this medium carbon steel and say create copy, and just name it medium carbon steel, my properties, create a copy, and just make modifications here and save. And once you save new material or modify material, it will be in your library and you can reuse it anytime after that. There are the couple of things I would like to point out here. So first of all, CENOS simulation software is designed specially for induction heating, and that's why there are all nonlinear properties here, because we know that nonlinear properties are pretty important for accurate calculation. So let me demonstrate that. Like, for example, for electric conductivity, we just go in and you can see this is the table of values. So conductivity depends on temperature. You can easily just copy this and paste from Excel sheet if you have, and create your own material as well. But of course, if you don't like it, you can also select it as a constant value, or even we allow to define expressions. The most important here is BH curve. So you know that magnetic properties, especially for ferromagnetic materials, are nonlinear. So you can define here a table, the BH, or if you want to save some calculation time, because this BH curve simulation will require some iterations, it will take slightly more time. You can just simply disable that, and instead of BH curve, you can enter here magnetic permeability, which represents your estimated magnetic field. The same goes for temperature dependence. So you know that ferromagnetic material just lose their ferromagnetic properties over Curie temperature. Just simply enter here Curie temperature, and your calculation will be very accurate. However, if you are sure that you operate under Curie temperature or above Curie temperature, you just simply can opt it out and save some computation time on that as well. All right, so that was the second step. So select material. And the third step is boundary conditions. So in this case, the most important is cooling conditions. In this case, we select the convective and radiation. For the convection, so it's heat transfer coefficient you have to define, and this heat transfer coefficient represents natural convection, or just no cooling except just natural movement in the air because of rotation of the part. However, if you want to simulate quenching, it's not a problem at all. You can simply change this heat transfer coefficient to the value which represents quenching. In our documentation, there is a table. You can look in the table, find your quench liquid, estimate your heat transfer coefficient, and put it here. Moreover, instead of constant value, you can define here a table. So, and this table, so this is depending on temperature, but you can also select depending on time, and you can simulate like stepwise a program, like program your simulation. Let's say, for example, for the first 2 seconds, we have 1000 watts per square meter Kelvin, which represent no quenching. And from the next time step, we select, let's say, 30,000, which represent quenching, and it's for the next 2 seconds, let's say. So this is like stepwise function, and this program represent like first 2 seconds, no quenching, then quenching. Super easy. If we go to inductor, the same for inductor. You select here either current source or voltage source. If you have a power controlled converter, it's not a problem as well. You can there is an easy way how to deal with this program. So the description is in our documentation, or just let me know, and we will explain you in the one-on-one meeting. For the current, as well for the voltage, you can select the same constant value or table. And for table, you can do the same like we did with the heat transfer coefficient of quenching. For the first 2 seconds, let's say, is 13 kiloamps. And then you just, let's say, drop it to 0. And this will be quenching. If you want to resume heating after that, or if you want to change, let's say, let's go further, and from the next time step, let's say it will be 5 kiloamps, and so on. So you program the simulation like you want and do the simulation. It will be accurate. For concentrators, nothing to say here. You just simply select flux roll material, and actually that is. The last thing, you have to define some simulation control here. So our software works with the 2D geometries, 2D axial symmetry geometries, 3D like full models, and also sectors. By the way, instead of full 3D model, you can also simulate only slice using some symmetry conditions. This is very good for scanning applications, for example. So you will save a lot of simulation time, calculation time, just simulating slice instead of the full 3D model. And for slice, our software allows to apply symmetry boundary conditions on the slice surfaces. And our software will know that you select slice, then the calculation will be for slice, but it will be as you simulate the full geometry. In this case, it's full 3D calculation, so it's transient. Of course, you can also select steady state if you want, but in this case, it's transient 5 kilohertz frequency. By the way, you can also define frequency as stable, absolutely the same way like we described it for current and heat transfer coefficient. So then you select the simulation time or heating time. You can also use adaptive time step. So we do not recommend to use it for the huge 3D simulations because it might take you a lot of time in the beginning. But for some 2D simulations or simple 3D cases, you can use adaptive time step, and it will be very convenient for you. You can resume your calculation from the last time step. And the last thing actually here is, so this is rotation. And you can see we defined rotation, and this is velocity in degrees per second. You can also select RPM and RPS, it's not a problem. And in this case, so the full rotation of the spline CV joint was simulated. There are also one important option, which is not present in many simulation software. You can select either you want to calculate fast or accurate. So fast means really fast, but it's about 80% accurate. However, it saves you time. Accurate algorithm give you very accurate results, but it takes longer time because of different algorithms. Our customers do so they make several fast calculations in order to find the right design, and then they run accurate calculation to confirm their results. This is really good opportunity because it saves you a lot of time and give you opportunity to design quick. And this is pretty unique for our software. So basically, this was for the middle part. You can see how easy it's to set up simulation case. It's really take, let's say, 5–10 minutes, and you are ready to go for the complicated 3D geometry. The calculation of 3D geometry may take from 30 minutes to several hours. Sometimes it requires overnight calculation. But the good thing that you can run several calculations in a row, prepare several cases, and just run them one by one automatically during night, for example. And if it's overnight calculation, you just come in the morning, open your computer, and you can see results there, and you can make a design decision. So let's go back now. There is last thing I want to show you. Actually, you can see that we already were in the result part. We just walked through physical settings, and there is geometry here as well. Let me open the new case. And here you can see there are 3 ways. So you can start from templates. It's for fast calculation, fast estimation of very easy geometries like pipe, step shaft, or rod, and the simple solenoidal inductors with multiple windings. If you are interested in templates, you can go to our YouTube channel, CENOS Platform, and look there. There are good videos which demonstrate how it works and how easy it is. So if you start with templates, your engineer will be able to simulate the first, to see the first result in, let's say, 5-8 minutes, really. The second way is from CAD. So if you use any CAD software like Autodesk or SolidWorks or Solid Edge, you can save your geometry, 3D geometry in step file and open it here and work from this. It's pretty easy for that as well. You can also see some videos in our YouTube channel, CENOS Platform, how to work with the FromCAD. In this demonstration, I want to show you Advanced Geometry Editor. So it's built-in editor, which allow you to either make some modification of your geometry in this editor or build it from scratch. So let me open this interface for you. As I already said, there is slightly different interface because, again, we use the best of open source tools here. And this is the open source tool called Salome. It's a full 3D design software. We typically recommend to our customer to use SolidWorks or Solid Edge or Autodesk or Inventor for complicated geometries. However, if you have some simple things or you want to make some modification, you can use this software as well. It's not a problem. So you can see this is the 3D geometry of the CV joint with inductor and flux concentrators. I would like to walk to show you how to make modifications. This is pretty important here. So first of all, you can see here we selected here rotation. So we defined rotation as a variable, and that's why it appeared in physical settings part. So you just define there the rotation speed. So if we, for example, select the inductor, and I want to make transition, just to say, let's say, so this is Y direction. I want to shift it to some value in the Y direction. Okay, but instead of just writing here the number, I can write, let's say, distance and define this variable here, and then we have it as a variable. So we can make changes anytime and recalculate it automatically. Here, and actually you can see this is rotation here. But the same way, if we define distance there, there will be as well distance here. It can make changes of the value out of here. This advanced geometry editor, Salome, also allow to modify numeric mesh. So we just switch to the mesh part. Let me visualize here the mesh. So this is numerical mesh created automatically. Let's just make small inspection of it. So I want to clip that. I will select actually XY plane like this. And here I want to demonstrate you a very useful thing. So it's not common in simulation software, and that's why it's really make this software very good. I mean, you can see here what called skin layers. So in the skin depth, we have to make resolution careful. This specific tool allows us to make the layers. And this layer saves a lot of calculation time, because instead of just resolving this skin depth with the tetrahedrals, we can make these layers with the hexahedrals here, while just making tetrahedral mesh inside. So the same for workpiece. I mean, this approach is pretty simple. You just select here, let's say, inductor. Let's make modification here, and this is called viscous layers because it came from CFD, and it's just simple. You define total thickness, which depends on the skin depth, and you define number of layers and stretch factor as well. And actually, that will be, and you also add here some surfaces or just faces without layers. That means that these layers will be applied to all surfaces of this domain. And actually so this layer will be calculated automatically as well as other mesh. So this function allows you to save calculation time. And once you build this interface, or once you build this mesh, you can go to the next steps and make simulation. If you need to change some parameters, you can either change those parameters from the physical setup interface or go back here and recalculate. But anyway, it will be done automatically.
Thanks for watching. I was very happy to show you how our users save up to 80% of design time and cost. And now, I would like to know how would you use our software for your business. So click on the link below the video and download your free trial.